Everyone, my name is Sasha Rush. I'm a professor at Cornell Tech in New York City and a programmer at Hugging Face. This is a collection of puzzles I developed to help people learn PyTorch. Today I'm going to play through them and work through some of the ideas to build them in practice. It'll take us about an hour to go through about 22 puzzles. If you're interested, you can play along with this online. Feel free to stop or drop out at any point if you get the idea of how the puzzles work. I think it's more effective to go through these in practice yourself, but some people have been asking how I approach them or what tricks they might use when doing them on their own. So without further ado, let's do some puzzles. In today's lecture, what we'll do is we'll work through a series of puzzles that are designed to help you understand how tensors work in PyTorch and what you can do with them. So the idea of these puzzles is that they are all about broadcasting. And to make broadcasting work, it's really important that you know one rule. I kind of channeled my inner high school teacher here and wrote a poem about how it works. So here's the poem. There's a rule you should learn at long last. Combination of tensors the task. Dims right aligned, extra left ones assigned. Match pair dimensions broadcast. So the way it works is that when you have two tensors of different sizes, you can know predictably how the final tensor size will be constructed. You do this by right aligning the shapes of the two tensors and then basically just going down each column. If in a column one of the values is 1, it just takes the other value. So here it becomes 3, here it becomes 8, and then we add an implicit 1 to make everything fit. So the final size is 9 by 8 by 3. This will be easier once we look at some of the pictures. So this exercise is taken from a series of puzzles I made on GitHub. They're called Tensor Puzzles. You should be able to find them on Google. The way the puzzles work is that they have a very strict set of rules. We have to solve each of them in maximum one line of code, so we get less than 80 columns. And we're allowed to use a lot of the basic operations in PyTorch. So this includes matrix multiplication, arithmetic, comparison, checking shapes, and things like that. We're also allowed to add extra size 1 dimensions, and we're allowed to use indexing. You're not allowed to do anything else, so you can't view, sum, take, or use any of the special magic PyTorch functions. Everything is meant to be done from first principles. And you can start with two basic functions. So the functions we'll begin with are arange, which creates a vector with values starting from 0 and going up to a given number. So here we have arange 5, and that's equivalent to a tensor of length 5 with increasing values. So 0 I'll write as white, and then increasing values correspond to a gradient of darker orange colors. We can also look at what this would be as simply a tensor. So it's 0, 1, 2, 3, 4. And this will be the core building block that we'll use to kind of compute the rest of the puzzles. The second idea that we can use is broadcasting. So this is what I mentioned before. For broadcasting, we're going to basically take two tensors and apply some sort of binary operation. So let's say the binary operation is that we take two values, a and b, and we sum them together. What will it look like? Well, if 1 is a row vector like this, 0, 1, 2, that's a, and b is a column vector, 0, 1, 2, 3, 4, then when we broadcast them together, we get out a matrix where this top left value is 0, because that came from adding this and this to get that final value. Whereas this bottom value down here is 2 plus 3, so that would be 5. Here's another example. So let's say our first is a column vector, 0, 1, and our second is a row vector, 0, 1. Then adding them together gives us a 2 by 2 matrix with a 0 in the top left value and the bottom right being 2, 1 plus 1. So that's the main broadcasting idea that we can use throughout the puzzles. Finally, it will be very helpful to have one more function, which is known as where. You can think about where as a replacement for an if statement when working with tensors. Here's the math to implement it, but I think that's less important than what it actually does. So again, let's read down the columns. Where takes in 3 arguments. It takes q, A and B. If Q is 0, then it takes B as its final value. If Q had been 1, then it would take A as its final value. And we can actually do this and see, just confirm that that's true. So if Q had been 1, it would have taken A as its final value. What's neat about where, though, is that it can be applied to tensors. So if you take in two values, false and true, and you then have A and B, then in the first position, it will take B, and in the second position, it will take A. So that's how we compute the return tensor from those original values. Now, where can be a bit more complex because it can broadcast. So that means that if the original value that comes in is Q, and that's 0, 1, just as before, but instead of giving in two values for A, we simply give in 1, then this basically broadcasts into a two-value vector for this to work. So just to play out how that happens, so if this is false, then we go to B and get B's value. If it's true, we get A's value, which implicitly broadcasts as the final result. This can get trickier if you have multiple different size tensors. So here, where is a matrix, 2 by 2, whereas A is simply a single value and B is a two-value tensor. So let's play through all the cases. So this is 0, so that means I'm going to take B's value, which is blue, which is here. I take this one because I was in the first column. Now let's say I'm in the second column. Well, that's going to be A's value. There's only one value for A, so that gets pulled down here. We do this again, get A's value here, and then finally this wants B value, but it's the second column, so we get a 0 value here. You might find it helpful to pause the video and make sure you understand how these work, in particular to go through this last example to get all the full outputs of the broadcasting system. So where and A range are the two functions we have to work with, and from those we're going to basically build out all the other functions in Torch. Let's get started. The first puzzle is called ones. It asks us to implement a PyTorch function called ones that returns a vector of all ones. Now, to define this more formally, the puzzles give us a spec, which tells us how to do this in pure Python. So to implement this in pure Python, we would simply iterate for I equal to the length of our output and set that position equal to 1. We're then tasked to do this ourselves, but using only the functions we've been given so far. The puzzles also show us some examples of what we should do. So our target is, say, a vector of length 4, where every value is 1, a vector of length 3, and a vector of length 4. These will get more interesting as we go. So how do we do this? We know that I is the length of the tensor we need to produce, and we need all of its values to be 1. So to get started, we're going to probably want to use A range. So if we say A range I, that will give us back a tensor of the right length. So let's see what happens if we just return A range I. Okay, so it told us that our target looked like this, but our output looked like this. So we weren't exactly correct because ours is 0, 1, 2, and theirs is all 1. So we're going to either need to use a standard mathematical operation, or we're going to need to use the where function in order to make this work. So let's use the where function using broadcasting. So we can say where A range I is greater than -1, so that should be every position, return 1, otherwise return 0. So this first thing will be the right length, but it will always be true. That means we'll always get this second value and not this third value. So let's see what happens when we run that. Now we got the targets are all 1s, our value is all 1s, so we should be pretty good. Let's jump ahead and check. So here we are going to run our final test on this approach, and we got it correct, which means we get a picture of a cute puppy. Great, so on to puzzle 2. So for puzzle 2, we want to compute the sum of a vector. So obviously this is built into PyTorch, but we'd like to do it with the operations we've created so far. So again, we have a specification in pure Python. The specification is going to add up all the values into the first position of out. The function we need to implement, sum, takes a as an argument, which is a torch tensor of length I. We need to produce a torch tensor of shape 1. So a tensor with a single value that is the sum of the vector that was given to us. So to implement this, we'll utilize a dot product. So the sum of a vector is the same as the dot product with a vector of all ones. So let's use the ones function that we created. So this is ones of the same shape as A, and we'd like to dot product it with A. Now the one problem with this is that if we dot product these two together, we'll get back a scalar, but the specification tells us that we need to produce a tensor of shape 1. So we'll add an extra trailing dimension at the end of A. This is a dimension of shape 1. And then when we take the dot product, this will be I, this will be I. Those two will reduce, and we'll end up with a torch tensor of shape 1. So let's run that, and hopefully it works. Cool, there we go. We got the target value here, and ours, target, target, and target, target. So let's check that this runs for all example cases, and see if we got a puppy. Oh. It's a little bit of a weird one, but we got it correct. Cool. So the next puzzle asks us to compute outer. This is the outer product of two vectors. There is a specialized function for running this in PyTorch, but in practice we can implement it with what we've built so far. Cool. So here's how it works. So given two vectors, both which are row vectors, our target should be their outer product. So that means every one of these positions multiplied together gives us another one of the values. So let's see. So this is the first row, third column. So that would be this position is the multiplication of those two. We can see it as well here where we have two values, some positive and some negative. So if we multiply this by this, that should give us this position here. But this times this gives us this position there. So this is a kind of classic use of broadcasting. Here we have A, which is a vector of size I, B, which is a vector of size j, and we need to produce something that's I by j. So let's implement it. So we're going to return something where we take the product of these two. A should be first and B should be second. So we write A, all its values go first, times B, all its values go second. We multiply those together, we should get something that's I by j, and we can run test outer to get our output. So here's what it looks like. We'll get a small picture back. Here was the target, here was ours. They look pretty good. So simple, a few lines of code allow us to compute an outer product of two vectors. Let's confirm by running our test. I think that's my favorite one. Next puzzle, diag. Here we want to compute the diagonal vector of a square matrix. So basically pull out the diagonal vector of the matrix itself. This one's worth going into a little bit more detail. The way it works is that given a matrix like A, it has to be a square matrix. We want to produce a vector that corresponds to the diagonal. We can see the implementation in the spec. It's basically ignoring all the values except the ones along the diagonal, II. So how do we do this? Well, this is worth several different approaches to think through. The easiest way is to basically understand how indexing in PyTorch works. So the way indexing works is that if you give a tensor as indices to two different dimensions, it will create a new tensor by basically zipping those together and pulling out the values. So if we say A range, A dot shape 0, that basically corresponds to each one of the rows in A. But if we also say A range, A dot shape 0, here, that corresponds to all of the columns in A. But by passing them both together, we'll walk along both simultaneously to produce an output vector of the right shape. So if I run this, we'll see that I get pretty good results. This goes along this diagonal, and this diagonal here. Now there are other ways to implement this function, but I'll leave those up to you to think through and try to come up with other approaches. Let's check our test. Nice. This one looks like a cat. Well, I guess there's a dog there too. Here we have a related matrix. This matrix is known as I. It's the identity matrix of a given size. This is a critically important matrix for doing some of the later problems in the puzzles, but it also comes up a lot when implementing neural networks. Cool, so here's the spec for I. We simply set the diagonal values all equal to 1. This is a function that only takes a size as an argument, so we get in a size j. We don't have to mess around with any other functions. Cool. So how do we do this? Well, we know that we're given j, so we probably want to use a range to at least create something of the right size. So let's do a range of size j. That will give me a vector of size j. I need some way, though, to actually create the matrix. But we can do the same trick that we did for outer, which is that we can basically just put these as row values and not as column values. We do this by inserting a dimension of size 1. When we did outer, we then did another a range that we multiplied it by. So in particular, we can write this explicitly like this, and this corresponds to one column that is of counting upwards multiplied by another column, by the others counting outward. So this corresponds to our rows, this corresponds to our columns. So let's see what that looks like in practice. Okay, so we get a matrix of the right size, that's good, but the values don't really correspond to each other along the diagonal. So to make that work, we're going to have to actually compute the right values on the diagonal. There's several different ways to do it, but maybe the easiest way to do it is with where. So we want a where statement that is equal to 1 in one case and 0 in the other. So two different cases, one is 1 and one is 0, and we want this to only be the one case along the diagonal. So the easiest way to do that is to simply come up with a comparison operator where rows is equal to columns, which would just correspond to an equals equals there. We can run this and see our output. So this gives diagonal, diagonal, and produces our value. Now we can make this even simpler if we consider the fact that we actually didn't need to do this here. If you remember the rules of broadcasting, it will automatically add leading dimensions of shape 1 if they are needed. So we can remove this and basically get the same result. There we go. We didn't actually need to use where for this equation. In fact, we probably could just remove it entirely and hope for casting to work. If we try this here, we can actually get a matrix of the right shape and get our output values here. Now, in various different versions of PyTorch, this might actually be a Boolean type as opposed to an integer. So you might also want to put something in like that to cast it into the right type that you're interested in. So this will give you something that you're sure will be an integer in practice. Okay, so this is pretty simple. It's a little mysterious that it works very well, but it's worth being able to read these in practice to understand how they work. So we can run this to check that we did everything correctly. The next puzzle is TreeU. This computes an upper triangular matrix. This function is critically important when writing things like a transformer. It's how people implement functions such as causal attention. but it's also kind of just a standard linear algebra operator that's worth using in practice. So it's going to actually compute a matrix where it has 1s in all the upper triangular components and 0 in all the lower triangular components. Note that the diagonal is also 1. The spec for this is a little complicated. It will be much longer than our implementation using tensors. So let's think about how this works. We again need to produce a square matrix that's j by j, and we're simply taking in the final size as an argument. So let's do the same trick that we did last time as a way of starting. We'll define a where clause where we get access to a range j times a range j, or let's say they're equal to each other. And we're going to return 1 in one case and 0 in the other. Now to actually make sure they're the right shape, we will start with colon none there. So if I run this, I think I'll get something out that's the right shape, but we just have the diagonal filled. In practice, though, we want this upper part filled as well, so we have to make sure those values return true. And it seems like what it corresponds to is that we want the column values that are greater than the row values. So in this example here, the column values must be higher, they should be filled in, whereas the row values are not. So to do that, it looks like we need to think about which is the rows and which is the columns. This here is the rows, it comes first. This is the columns. So we want the columns to be greater than the rows, greater than or equal to the rows. Okay, let's run that. So this looks pretty good. We check that the columns are greater than or equal to the rows, and it all worked out nicely. Again, we can simplify it by doing 1 times and producing our final value. Okay, next let's implement cumulative sum. So this is the sum of all the positions up to the final position in our output. So let's look at the spec first. So it's going to run over each of our input values. It's going to keep a running tally of the sum so far, and it's going to set that value to the output value. We can see examples here. Here we keep on adding in negative values, it gets darker. Here we add positive values, it gets lighter. Okay, so this is another sum example. So I think we want to look at using some form of dot product as the way we compute this. This is going to be a bit complex, so let's actually look at an example here. So up until this point, we've basically computed sums by using dot products. We set all our values equal to 1, so let's just say that's all black. And the way we did a dot product is we simply did each position by each other, and that summed everything up. So if all the values are 1, then we get a sum of everything. Now, in practice, this will give us the final value that we need in our output. But we want to compute all the running values as well. So we'll do that by also using dot product. So we'll want to compute another dot product that only takes into account these first 3. So 1, 2, and 3, but not this final value in its output. So that means we need this part to be, say, not filled. Let's see, how do I do that? Okay, great. And then we keep on going upwards to compute the previous dot product where we only take into account the first 2 values. Cool. Now I think you can see where this is going. We want some sort of triangular-like structure to take into account the previous values that we used. If we can construct a triangular shaped matrix, it can basically compute this for us. Now, we had that in the last section where we had tree U, but let's just construct the one that we need in order to compute the cumulative sum. So we'll say we're going to do a, well actually first let's give a variable. We'll say I equals a.shape0. It'll make things less verbose. Then we'll do an a range up to I. We'll say that that's the row values. And we'll say equals equals a range I. That's the column values. Now we're going to say a at because we're going to be doing multiple dot products, otherwise known as a vector matrix multiply. So we just need to decide where the values will be 1 and where they'll be 0. So let's just start with this. So in this example, it's a vector matrix multiply with the identity matrix. So that'll just keep the values. So that just pulls these down. But we don't want that. We want to actually sum them up as we go. So in this example here, the rows of this matrix are going to correspond to A. So we want to keep the rows that are less than or equal to the columns. So the rows that are less than or equal to columns should give us something like our diagram. Looks pretty close. Here are our targets. Here's our values. By doing this, we get our outputs, and we can see if this passes our test. Looks pretty good. So just to go back and review what we did, we wanted to do multiple dot products to sum up the values. We did this by constructing a triangular shaped matrix. That matrix made sure that we summed up the values that were less than or equal to our current row, and that's how we got our final cumulative sum. Cool. So let's keep on playing with the same idea. This is from a function called diff that computes a running difference of a vector. So let's first see what this is. So it looks like at each position, it computes AI minus 1. So it kind of just computes the first order difference of a vector. So here we have a vector that's all negatives, but some of these values are positive because this is 0 and this is negative, so that becomes a positive value. Again, we have input vector A, although this time we actually are given as well the size to work with. Cool. So let's think about how this works. In particular, we should think about boundary conditions. So it looks like the out value is just equal to A0 to work with here. Okay, so we're probably going to want to compute an A range of length I, and we're going to want to use that in our construction. So let's say we just do A range. That's just our standard value. But we could also do A range I minus 1. So that should give us all the values before. So let's run that and see what it looks like. So it looks pretty close. So this one almost was exactly right. This looks pretty good, but this is slightly off. So I think that's because of our boundary conditions. So we have to make sure that those work as well. So I think the problem is here that we are going over the line to actually get the -1th value kind of wrap around the matrix itself. Cool. So let's set that up so that we can have a different value at that position. I'm going to write this just as a where clause. So most of the time we want this value, but some of the time we want 0. And we have to determine where that is. So it seems like the only time we want the second part of this clause to be 0 is at position 0. So we need to check for position 0. We'll do that by writing another A range. And we'll say as long as A range is not equal to 0, then we just do what we did before. Otherwise, we subtract 0. So running this, I get what I had before, a nice match at these positions. There's probably other ways to do this. We could have constructed a matrix or probably many other approaches, but this is relatively readable and captures the conditions of interest. One thing to note, though, is that we can make it simpler. We don't need this, right, because this is just A. Can we make it any simpler on this side? No, I think this is probably about as good as we're going to get. Okay, let's run the test. Nice. Okay, so VSAC is a particularly useful function in PyTorch. It's going to allow us to create a matrix out of 2 vectors. This is often used when you have kind of 2 parts of code that you'd like to do in parallel by running matrix operations. Okay, so given A and given B, we're going to create a target with these on top of each other. So one thing that I find is kind of a common mistake for these sort of functions is that people assume that you have to implement them by kind of literally figuring out how to smash together the two vectors. In practice, though, I often find it better to first create a vector of the size we want and then literally use broadcasting just to pull values forward. So let's go about that path. So we first just need to create something that's the size we want. So the size we want is going to be 2 by whatever the original lengths were. So we'll have one A range that corresponds to the original length. Let's give ourselves an extra line just to pull that value out. And then that will be our columns. So we don't need this, but we can do it just for remembering. And then our rows are going to be 2 rows. So if we just multiply these together, we'll already have something of the right shape that we're interested in. So here's the shape of ours versus the shape of the target. Now, of course, the values aren't even close to being right, but still they're pretty good to get started with. Cool. So once we've done that, we can use where to pull the values forward. So we'll say where, this statement, and in one case we'll pull from A, and the other case we'll pull from B. So this at least gives us the values from A and the values from B to get started with. Okay, so we still have the right shapes, but we're pulling forward the wrong values that we're working with. So what do we need it to do? We want it, if it's row 0, to pull A, and if it's row 1, to pull B. So how do we actually do that? Let's make this, instead of A range, 1s. So that will be all 1 values. And then this will either be 0 or 1. Then we can just say equals equals. So in row 0, it will be false, and in row 1, it will be true. Now the only downside is that then these need to be flipped. So we want this to be true and this to be false. Let's run that. Great. So it looks like this worked out nicely. We had to first just create the shape that we were interested in, and then figure out some way to make it true and false in these cases. Seems good? Nice. So in the roll function, we're going to use a circular shift. That means we're going to change the original values and shift them around by a given number. So specifically, it looks like the spec for roll is such that every value gets moved by 1, and then we make sure it wraps around. So in this case, everything gets moved over by 1, and then we wrap around. Cool. So I think there's also a couple different ways to implement this function. Just as with cumulative sum, we could construct a matrix and do matrix multiply. We can also use indexing like we saw before. So in particular, we're going to want to create a vector to be our index, and we'd like that vector to have the same length as the original, so we keep the same size. So this should be I, and we'd like to return I. So let's do that. So if we say return A range I, that will return the same value that we started with. However, we would like to roll this, so we'd like to do a -1 here to shift everything 1 to the left. Oops, so this failed, so let's do +1. I think I did the wrong direction. Oh, but now we get an error. I guess that makes sense because this is an A range to I, and then we add 1. Now we're going to be out of range in terms of our original A vector. So we have to think a bit through how that would work. In particular, we have to just make sure when we get to a higher value, we restart from the beginning. So the most typical way to do that is with some sort of modulus. So we'll just mod by I. Modulus should be fine in terms of running as a PyTorch operator. So we can run this, and that looks pretty good. So when we go over the size, we take a modulus and we wrap back around to the beginning. kind of still summer here in New York, so that looks pretty good as a kind of winter day. Cool. So puzzle 11 is flipping. So in particular, flip is what they call reversing a vector. This will require us to just produce the vector backwards. This is another one of these puzzles where we can implement it using a matrix operator, or we can implement it using clever indexing. So let's do the indexing one, just because it's relatively straightforward. So here is our vector. We'd like to produce the reverse vector. That means we have to produce an index that's going to index in the reverse order of what we were given. So we start with A. We're going to have an A range of length I. We would like this to go in the opposite direction. So we'll do I minus A range minus 1. Great. Okay, next up we have compress. This one's a bit harder than the others and is going to require to use a lot of the tricks that we've seen so far. The way compress works is that it's masking plus padding. We're going to have a mask G, which will determine what entries to keep. But we're going to slide all the entries over so they're left aligned. So this goes here, and this goes here, this goes here, and this goes here, and then this is kept in this position. So in order to do this, we're going to have to use, as I mentioned, several of our earlier tricks. So in particular, let's think first about how we determine what position we're targeting. So if we do that, we can see that this should go into position 0, and this should go into position 1. That can be calculated by treating the Boolean mask like it were an integer and computing a cumulative sum. So if I run this, I'll basically get the sum so far of how many things that we've kept. Now I'm going to want to subtract 1 from that to get the actual position where it ends up in. So here this will be position 0, and then this will be position 1. Now starting from there, we want to get rid of all the entries that have no value. So those basically need to be able to go away. So we can do that by computing a where this is using our input G and saying, let's say, -1 for the ones that don't have an entry. So these are all -1. Here, these are all kept, and then these are all -1. So that basically lets us remove the ones that we don't need. Now, let's take this one step further. So these positions, they're going to correspond to where things in the row get mapped to. So we can extend this into a row vector like this, as well as make this a row as we go. So this basically will turn them in this form. Now we do this because in order to actually map from G to our final value, we have to actually treat this as something that will allow us to map from one vector to another. We'll do that by actually creating a matrix that maps from our input V to our output. So let's say this is V, and then this is the actual matrix we're going to compute. We'd like to be able to map from, say, the second position in V to the first position in our output. So to do that, we'll actually create a matrix that has 1 in this position and 0 in everything else in that row. That way we can just multiply this matrix by V to move things around to the final position. This matrix will be all 0s or 1s and only have at most a single value in each row. So to do that, let's make sure that this is the position that we want to go to, and we also make an A range of the position we started from. And let's multiply those two together. So this will be basically the matrix that we were describing before. So here, this position should go to here, here, here. Here we go again, this position's here, and then these get thrown away. Let's get another random seed just to get different outputs. So this is easier to see. So this position 2 gets mapped to a target position 1 here, and similarly in this matrix as well. Now, we can actually multiply this, do a matrix multiply from our original vector by this matrix to get our output. And then we want to turn this -1 into a 0 because we actually don't need negatives in those columns. Awesome. This looks pretty close. Let's try one more time. Great. This was a pretty hard one, so let's review what went on. We were basically creating a matrix that maps from V, the input, to our output. There were two components to that matrix. We wanted to zero out all the rows that were masked out, and the others, we wanted to make sure they got mapped to the right location. This part in here ensures that they map to the right location, and this part here actually calculates what that location is by summing up over the mask. Let's check that in practice. The next couple of puzzles will have similar padding challenges. In this puzzle, we're going to basically eliminate zeros by changing the size of the vector. So here's what it looks like. Starting from A, the blank, we're going to produce the following or the following. So it can do one of two things. It can either remove or add things based on the sizes. So here is our input vector. Here's size 1, here's size 2. Here is our output vector. So the first instinct for this sort of problem is to treat it with where. If we could say where A or 0, that could make things work pretty nicely. So specifically, let's say this were the where is a range of whatever our output size is going to be. And if it's less than, say, our input size, we'll keep the values. Otherwise, we'll provide 0. The problem with this is we're going to run into an error because this is length j, whereas this is only length I. So we can't have things in our where clauses that are of different lengths. So we have to be a little bit smarter than that here. This looks pretty good, though. This will broadcast. It's just the problem of this A to start with. I guess this does work if it's padding in one direction but not the other. So let's get that started with. So if this is going up to I and then that's j, that will let us handle some of the cases. So let's try that. So that'll roughly get us down to the right size, but we'll have these extra zeros to handle. Okay, so if we're going to change sizes, I think we're going to need to use our matrix once more. So we're going to need a matrix that's I by j in order to compute this transformation. So let's actually construct it as a matrix. So we're going to start A. That'll correspond to the rows. Those will be I of them. And the columns will correspond to j. So we have to actually create a matrix using an A range I and an A range j to actually produce our final values. Now we can start with these two being equal to each other. That will move all the i's to all the j positions. We have to make sure we're doing a nice outer product in order to make that work and actually compute these values. So let's run that. Oh, again, we're going to get an error because of the silly PyTorch casting. So I'll do 1 times and actually get our values out. Oh, wow. So this seemed to work right off the bat. Let's look at what we did. We said the rows are A range to I. The columns are A range to j. That ensures we map from I to j. And we keep them when they're equal to each other. So if we actually look at what this matrix looked like, it should be an offset diagonal that corresponds to just mapping things over. Here we do A at and get our output. Next up, sequence mask. This is an important function when doing natural language processing. We're assuming here that we have some values as our input, and we have some lengths. And these lengths tell us how many of the elements of the batch to actually use. So here, this is 1 and 1, because we only keep those two, whereas these two are 0, so we keep nothing for those rows. This is going to be another where-based kind of problem. We're going to basically need to mask our values with 0. And the key question is, what do we set the where clause to be? So there's definitely going to be an A range I, which corresponds to the first position of values. And there's also going to be an A range j. Now we need to actually get these. So let's say ij is equal to values.shape. Cheat a little bit here. And this should at least give us something to get started with. So this will be wrong, but each of the positions do come out. So what is it that we want to actually keep? We want to keep it when a row is less than the corresponding length value. So this is the length value for row 0. So that means there should be something here. So that means that this will probably be less than or equal. And it's less than or equal to the row value to whatever the length was at that position. This is the columns. Sorry, this should be the other way around. Greater than or equal to of, and then this should be, instead of A range, this probably should be length, because that corresponds to I. Length is greater than or equal to that A range. So let's try that. Cool. That looks pretty good. It looks like we're off by 1. So that must mean because the spec is not greater than or equal to, but simply greater than. This looks good. Let's try it one more time. OK, great. Let's check that one. Nice. These are randomly generated, so we got that one a couple times, I think. Cool. So in bin count, we're counting the number of times a particular entry has seen. This is a particularly useful function for building histograms or other sorts of statistical counting. So let's make this a little smaller so you can see it. So we have bin count that we need as our output. We will construct it by basically counting up the number of things in each position. So here we have the value 0 3 times, so this is 3. Here we have 0 once and 2 positive values. I'm guessing 1 and 2, so we have those all positive, etc. So basically counting up what has been seen so far. So here is our input. It's A. And we basically need to transform these values into their locations and then count them all up. Cool. So how should we go about doing this? This is another case where it would probably be pretty useful to turn these values from their individual values into rows in a matrix. And what we're going to do is we're going to do that by using, let's say, one of the matrices we've created so far. So I'll do it using the I matrix. So we have I, which is the identity matrix. And if I compute an identity matrix of size j, j is basically the output length, then I can index that by A, which is these input values. So let's look at what that looks like. So basically what this does is it turns each one of these columns into, each one of these columns into a row of this matrix. So let's try that one more time. These are a little hard to differentiate. So you see how there's a 0 here? It's the third row. The third row, 0th column now has one hot vector, whereas the fourth has the value 1. So basically now this trick turns our input into a one hot vector in each of these rows. In order to compute the bin count, we now just need to sum up the rows to get these final values. See how that works? So to do that, we'll use our sum function. We created that earlier. If you remember how that worked, all we did was we did a ones with, in this case, it would be I, So it'd be a dot shape 0. And we reshape that as, oh, actually, I guess we don't need to do that here. Let's see if that works. Oh, I guess it doesn't. So we reshape it. So this is, let's see what this is. So this I is an I by J matrix. So we want to do it from the other side. So 1s should be a dot shape 0. That's I at i's. Looks pretty good. So this part, you should read that as taking a sum over the dimension corresponding to I. And then this thing is an I by J matrix, and we need to produce a J matrix as output. So that's a pretty simple way of doing bin count, transform to 1 hot, and then sum up. Scatteradd is one of several functions implemented in PyTorch that are efficient for computing various sorts of discrete lookups using matrices. In our scatteradd, we will have input as a set of values, and then a link function that tells them where to go. Again, this is a little harder to see with these pictures, but it does give you a bit of a sense of what this does. Here's what we do. So we have this link that tells us where things go. So for each of the values, out at link plus values j. So here, these are all linked to 0. So most of the values go there. And then this one points there. So it goes through, or this one goes through there. And then here, this goes here, etc., through this data. Cool. So I think this is another one where we can do using some combination of one-hot vectors and matrix construction. So let's see. So we'll start with values, and we're going to add it by something that has to be I by j. So that's the matrix we're going to construct. So we have to construct an I by j matrix. So let's transform link using i's. Let's look at a little bit closer what that did. So I, j link tells us basically where each thing should map to. And then we do the matrix multiply with v, or values, at i's. We'll take these values, multiply them by this matrix to get our targets. So when we run that, we get our nice outputs, and we can then check that it worked. Okay, flatten. In this function, we're basically going to take a matrix and flatten it out. That means we're going to transform this to each of these individual lines of this form. This can be done with, again, matrix multiplication or fancy types of indexing. Maybe for this one, we'll do the indexing approach, just because that will change things up. So here we're given in a matrix A, it's I by j, and we want to return something that's I times j. So to do this, we need to create this longer output. So let's first make an A range that's I by j, or I times j. That'll be as long as our output here. So we get kind of the same output, but different values. Let's actually index A with this, so that way we can basically pull out the values we need. So I times j. And the main trick here is that we're going to have to produce the right index at the right time. But before we do that, let's just do it a dumb way, where we will mod this by j and this by I. That way we ensure everything's in bounds, and we at least can see that this is the right shape. Great, so now we have the right shape, but the wrong values. So how should this actually work? Well, I think on this one, we basically have it right already, that every time you go, you should be moving along the columns, and we want to be modding by j each time. However, this one is a little trickier. Here we basically want to count how many rows we've passed over. So I think the way we're going to do that is every time we go j steps, we switch to the next row. So we can do that by integer division by j, and that will ensure that we kind of only go to a next row when we've done j steps. So let's run that. Get a warning here. I think, though, this is still correct. Let's see. We can jump ahead and just check without that warning. Let's see if we get our dog. Cool. Yeah, I think that's correct here, too. I think this is a PyTorch bug that got introduced. We can try to correct that, but I think this is mainly the right method for this function. OK. Linspace is an important function for graphing. It's kind of like arange, but instead of giving you just discrete outputs, it allows you to step between any arbitrary two floating point values. So here's the spec. So we're basically going to do a for loop, but ensure that the points in the for loop are in between I and j, and that we're doing steps of length k. So for this, we're basically just given two values, I and j, as well as the number of steps we need to make. And then the final output is the number of steps themselves. So these should always be kind of increasing in this manner. So the spec here is basically given to us above. We know that we're going to have to create something of length n. So let's do that right off the bat. So length n. And then we're going to basically transform it with the same steps here. So this becomes our k. But we can just copy this down. Let's just call this k so it looks like the spec. Cool. And then this length out is just n, n minus 1. And in general, this trick works pretty nicely. That if you have a for loop you want to transfer, you just make an arange. That becomes like the range of the loop, and that substitutes in for k. We can just copy that directly in to obey the specs here and get our output value. I think this should work with casting in PyTorch. Yeah, it looks pretty good. Let's try it one more time. Great. So we can run this test over our linspace. Okay, this function is called Heaviside. Actually, don't know if that's the right way to say it. Let's look at the spec. The spec here is that we're given some input. There are two conditions. If our current value is equal to 0, we basically put in the b value. Otherwise, we put in the following value. Checking that that is greater than 0, it will be 1. Otherwise, it will be 0. So let's look at an example. So this is negative, so it's not equal to 0, which means that this should be 0. This is positive, not equal to 0, so it will be 1. And then if it's 0, it's just this value getting pushed through. So I think this is one where we can utilize something like where to implement this if statement. So the where is going to be conditioned on the value of a. So where a equals 0, just like the loop above. We're just going to basically translate this if statement. If it's equal to 0, then it's b. Otherwise, we'll say greater than or equal to 0, and we'll multiply that by 1. That's the equivalent of this int statement above. So let's run that. Nice. Beautiful. Okay. I feel like we're making progress here. I think we're getting near the end of the puzzles. Some of the middle ones are some of the harder ones. Some of these later ones are just kind of using the tricks we've built up so far. So this is the repeat function. We're going to basically be just repeating the same value multiple times. So in particular, we're going to take a row and then kind of repeat it down multiple times. Okay. We can implement this one of several ways. I think probably the easiest would be to just use a where function again. So we're going to have a where function, and we basically need to create a predicate that's always going to pull from A and never from B. This will let us do broadcasting in an easy way. The where function is going to have the a range of over d. That's going to be the rows of the output. Oops. Then it'll be the rows of the output. Actually, we just basically always need it to be true. The broadcasting with A should work automatically. So instead of A range, let's just make this ones. 1, was it? Let's try ones equal 1. Oh. Maybe my broadcasting here is failing. Let's try to do it explicitly. Ones, D. Let's try it one more time. So if we do ones, is that? Oh, I see. D is given to us like that. Huh. Actually, I don't know what's going on with D here. Let's just, oh, what a funny bug. After all that, get a bug like that. Funny. Okay, so here's our ones, which is D value long, and A is our output. Okay, so why does this work? Well, ones is just going to be a row vector, so it'll be D by 1, whereas A is going to be I length. So A and this will broadcast, which will produce the repeat here. So that's a nice way of doing this. I think we can actually make it even simpler. So let's make it ones, like that, and just times it by A. So this is like an outer product of A with ones. Cool, so that worked really nicely. We can probably even just do it explicitly using our outer, and that can be even shorter. Great. Yeah, I don't know how to get any shorter than that. It's a kind of nice way of doing repeat. Okay, our last implementation is bucketize. Bucketize is a fun function that's also important for computing histograms. The way it works is the following. You're given a bunch of values, v. You have to transform them into a discrete number. The discrete number corresponds to where it fits along these boundary points. So these points are in increasing order. And in this case here, this value was greater than at least the first one of these, so it's positive, but these two are less than everything, so they're 0. So we have to be able to compare v to each one of these boundary points. We're going to do it in a brute force manner. That means we'll simply compare each v to all of these boundary points, and then just count up how many it was greater than. So to do this, we will simply compare the two. So we say v will be row vector, and we want to check how many boundaries it is greater than. So that'll correspond to the column vector. So we have rows, columns, corresponding to how many it's greater than. So in this case here, the first one is greater than 2, so it's greater than both of these, so it should have a value of 2, whereas this first one is greater than 3 of these, so it should have a value of 3. So this corresponds to just needing to sum up over the columns. So this was the first thing we did, was we take a dot product along ones, which were each of the columns. So the columns here correspond to boundaries.shape 0. So we should be able to just add these together. We do need to ensure, though, that this first is an integer. So let's run this. Looks pretty good. There might be an off by 1 error here. Let's try a couple more. Yeah, so this is should be maybe greater than or equal to. Let's try that one more time. Yeah, that looks better. Cool. Okay, so I'm not sure there's a check for this one either. So let's consider that correct. At the end of the puzzles, we have a little speedrun mode. This basically will tell us how well we did. So we can compute, let's see, over all of the ones we computed, how many columns we used. It seems like by far the hardest one for us was compress. That took 78 columns. A lot of the others we did a lot faster. I don't know of a better way to do compress. We spent a lot of time on that, so hopefully it was pretty close to optimal. Where was that? That was here. Be curious if anyone else figures out a way to do that better. I think possibly we could get away with not having both of these as none, but I think it's pretty close in practice. Cool. So if you're interested in these sort of puzzles, there are a bunch more where this came from. If you go to GitHub, and I think the latest one was called LLM Training Puzzles. You can find it here. This is kind of more complex training puzzles to work with, and we have links to all of the various different puzzles that we've released. In particular, the GPU puzzles seems to be the most popular. I think people have gotten a lot out of these, and hopefully I'll make a YouTube video about them in the future. So thanks very much for listening, and hope to see you again.